Okay, we want to construct the graph of f of x equals quantity x minus 2 squared times x plus 3 quantity squared times x minus 1. Well, it's easy to see where the zeros are, and that's where we usually start a graph, find the zeros and the intercepts, the y-intercept. So the zeros occur at x equals 2. The multiplicity is 2 because we have x minus 2 as a factor twice. Now we've shortcut, put that in a shorthand where we do x minus 2 squared, but that means x minus 2 times x minus 2. So x equals 2 is 0 for this thing, and it occurs twice, so it has multiplicity 2. X plus 3 gives you a 0 of negative 3, and that has multiplicity 3, because of course you got 3 factors of x plus 3. And then you have x minus 1 with its multiplicity of 1. So you have a point here, a point here, a point here, and the function has to go through all 3 of those points. Now, when we did it in class, we hadn't constructed the shape of the function, but we do have a rule that says we have a 0 of multiplicity 3, then the graph goes through that 0 as some transformation of an x cubed function with its vertex at that point. In other words, with the x equals 0 point of the basic function translated to this point. Now this would be multiplied by a negative number, vertically stretched by a negative if you use my terminology, or reflected through the x-axis and then vertically stretched if you use the terminology of your text. So that's the rule, so that's the way it looks. Now I'm going to give you a little more explanation of why it looks that way, so you don't need to remember a rule. You can actually understand why it looks that way and construct it that way, but it's up to you which way you want to think about it. Okay. Then at x equals 2, the 0 is of multiplicity 2. In other words, this thing acts like a multiple of x minus 2 quantity squared in the vicinity of x equals 2. I'll explain why that is, but here it is. And of course, quantity x minus 2 squared is just a parabola horizontally shifted so the vertex is at x equals 2. It's on the x-axis at the point 2, 0. So it's acting that way, but it's going to be a multiple of that. We'll see how that works, but you can think of it that way, just as you can think of this as being a transformation of the quantity x plus 3, the quantity x plus 3 cubed as being a horizontal shift of the x plus 3 function, and then you have a vertical stretch. And x equals 1 has multiplicity 1. Well, the graph of y equals x, if you replace x by 1, if you replace x by x minus 1, shifts the graph a unit to the right. So it acts like the graph of y equals x, but passing through the x-axis, not at the origin, but at x equals 1. Well, okay. Now just a little bit more about how I can say what I said. If x is near negative 3, then quantity x minus 2 squared times quantity x minus 1, in other words, this times this, everything but the x plus 3 cubed, is near negative 25. Why is that? Well, because if you plug in negative 3 for x, you're going to get 25. And actually, you kind of don't. You get negative 100 because x minus 2 squared is negative 25. Put around line to people in class right and left. So let's just fix that. So that's going to be negative 100. I'll let that dry just a little bit and then I'll fix it. Okay? And I'm going to have a negative 100 down here too. So I'm going to write those in. There's negative 100. And there's negative 100. Now, what I said is true. Okay, well, again, this is near negative 100, and this is this times this, so that f of x is close to negative 100 times quantity x plus 3 squared. And negative 100 times quantity x plus 3 squared is just the x plus 3 cubed, I'm sorry. Negative 100 times x plus 3 cubed is just the x cubed function, vertically stretched by factor 100 and reflected through the x-axis, and then shifted negative 3 units in the x direction. So this thing's very steep because of the negative 100, but of course on the scale of my graph it ends up looking like this. Okay, then similarly, if you look at the x minus 2 squared function near x equals 2, just in this small vicinity of x equals 2, x plus 3 squared times x minus 1 stays close to x plus 3 cubed times x minus 1, stays close to 125 times x minus 2 quantity squared, because if you plug in 2 here and here and evaluate this much, you get 125. Okay? Now, if x moves a little bit one way or another from 2, yeah, that's going to change a little bit, but it's not going to change that drastically if you don't move very far. Okay? And what do we mean by very far? Well, there's a deep question that we're not going to talk about here. Okay, so f of x has got to be close to 125 times quantity x minus 2 squared, within some small region around x equals 2. So it's going to be a parabola. Okay? And then it's going to be close to 64 times x minus 1. When x equals 1, this times this is 64. Yeah, it is. I don't, okay. And it's not, yeah, it is 64. Okay. Plug in x equals 1 here and here, you're going to get 64. So this is going to be close to 64 times quantity x minus 1, and 64 times quantity x minus 1 is going to have a straight line graph through here with some slope. Now the other thing is the y-intercept is negative 108, as you get when plugging in x equals 0. So I wonder if we draw a tangent line here and bring it down to the y-axis, if this is close to 64 times x minus 1, then the tangent line ought to be 64 times quantity x minus 1, which means it ought to go through the y-axis where? Well, that's 64x minus 64. If x is 0, it's negative 64. If this is negative 108, and that's what the y-intercept is that plausibly negative 64? Yeah, I think it is. Not exactly, because this is a hand-sketched graph. That's a hand-sketched tangent line. I don't know how accurate it is, but it certainly is plausible. That would be negative 64. Probably be a little lower than that, but close enough. Okay, well, there we have that. So that's a graph of this function with multiplicities and an explanation of why the multiplicities are what they are. Now, here's a graph. Okay, I just slapped this graph down, said here are the numbers, give me a function. Okay? Now, let me back up a minute. One more thing I need to say about this graph. If you expand these things, the overall behavior is that of the x to the 6th function, because you get an x squared from here, you get an x cubed out of this if you expand it, and you have an x here. You multiply those out, you get an x to the 6th. That's your leading term. So we're going to have a graph that acts like x to the 6th if you look at it a little further out from the region where you have the zeros. Okay, so it's like x to the 6th here, and it's like x to the 6th here. And x to the 6th is just like x squared, except it's flatter toward the vertex and steeper if you get past x equals 1. So graph's going to do this. It's just going to go off to infinity very rapidly after it gets away from these zeros. Okay, now let's go back to this one. That's going to be important. I thought I'd better mention it before we got into this one. I said it in class, but I didn't write it out. Okay, so here's a graph, and we've got zeros, 1, 2, 3, 4, 5 zeros. And this one looks like it's got multiplicity 1. This one looks like it's got multiplicity 1. This one looks like an x cubed. Now it might even be an x to the 5th or an x to the 7th, but it looks like an odd power of x here. So the simplest assumption is that it's a cube. Okay? Here it looks like a parabola, so that's going to be an x squared function. So, so we're going to have multiplicity 3 here, multiplicity 2 here, and then again, that looks linear. That's going to be multiplicity 1. So, what are our factors? To get a 0 at negative 6, we've got to have an x plus 6. To get a 0 at negative 3, we need x plus 3. To get a 0 at negative 1, we need x plus 1. To get a 0 at 4, we need x minus 4. To get a 0 at 9, we need x minus 9. This one and this one. You do that right? Yeah, this one and this one give you this one and this one with their multiplicities of 3 here and 2 here. Okay, so right there's our function. It's going to be some multiple of all this. Now, what's the multiple? Well, you can tell that from the y-intercept. Okay, but it's going to be some multiple, and we're going to find it very easily from the y-intercept. The multiple we're going to call a. So it's a, some number a, times all this. So we want to find a. It's easy to do. If x equals 0, now I've plugged in 0 for all the x's here, then this has to equal negative 12. So we just set negative 12 equal to a times what we get when we plug in 0. And we get, if I did the arithmetic right, and don't assume that I did, check me, negative 12 equals negative 2592a. So a is negative 12 over 2592. I estimated 0.0048. Now you can check my arithmetic because I'm doing these things in my head, and my head isn't reliable. It never was, but it's even less reliable than it used to be. So I get them a lot of times. I can do pretty well if I keep everything in mind, but my working memory is a little fuzzy, so you know, we'll see. You can check me. It's always a lot of fun to find me wrong. If I start being wrong even more, it's just going to get boring, but check it out. Okay, y is then this, a times all this, and I've written all this out here, but there it is.